So, good morning and welcome to our first lecture. So we will be looking at voltage, current, and resistance as our first topic of this unit. Now, I will start by giving an analogy that is related to these three electrical quantities, that is the voltage, the current, and the resistance. You can think of them in a different way, like where in my diagram this side, I have some water at the reservoir, and this water is being pumped so that it can go up to a higher position and also increase its pressure. Then once it is pumped, it gains what we call potential energy, and it also contains pressure that is able now to make this appliance, in our case is a dynamo, to rotate. When a dynamo rotates, what you get is electricity being produced. But as a result, now water turns the dynamo, but it again loses pressure and energy. Now it also requires now to pass through the pump again to get the energy and the pressure to be able to run the dynamo continuously. So so that simple analogy is likened to what voltage and current and resistance is in an electrical circuit. Now, in my diagram on this other side, I am having a battery which is supposed to drive current through the circuit, and there is a resistance, or we usually call this the load. This is the appliance that is absorbing the electrical energy and transforming it to some other form of energy. Now, what usually happens is current is actually the flow of changes through the circuit, and for changes, and the changes we are talking of in most cases are electrons. So for electrons to flow through a circuit, they need some energy, or they need to be given some pressure, electrical pressure, and it is the voltage source, which is the battery, that supplies that energy to make them to flow through the circuit. Now, when they pass through a resistor, the electrons will lose some energy that they were flowing with. And so the resistor causes the voltage drop across the appliance. So it's like this scenario where you want water at this point having high pressure, but when it rotates the dynamo, at this point it loses its energy and its pressure. Same thing here. You have at this point the electrical potential is high. At this other point, the electrical potential is low. So as current flows from the point of high potential to a point of low potential, some energy is lost, and so there's a voltage drop here. So that analogy helps you understand what current is to this scenario of water, the pump, and the reservoir. So a small exercise where you are told to match the analogy of water and the analogy of the voltage circuit. So what would you liken water to in this electrical circuit? How about the pump? What would you match the pump with in an electrical circuit? How about the valve? The valve is the gadget which makes water to either go on or off. In the electrical circuit, what would you liken it to? The pipe width, if you have a bigger pipe, you have more water flowing through it. In an electrical circuit, what would be an analogy for the width of the pipe be? And then we have also the pressure of the water would be likened to what in an electrical circuit. So it's a small exercise that kind of gives an analogy of water in an electrical circuit. So try to see if you can match those things correctly. Now, the next thing, let me first of all try and show this thing. Then the next thing I would want us to look at is a demo of what exactly voltage is. And we will be able to look at that in this short video clip. Just a minute. So I would wish that we watch this short video clip that explains in some detail what voltage is.
To understand how electricity works, we need to zoom in on atoms, the things that make up all matter. Atoms are made up of three basic particles. That is, protons, which have a positive electric charge, neutrons, which have no electric charge, and electrons, which have a negative electric charge. The protons and neutrons are tightly packed in the core or nucleus of an atom, while electrons move about this nucleus in regions known as shells or orbitals. Right now, this atom is electrically neutral, as it has the same number of protons and electrons. With enough energy, an electron may be stripped away, leaving the atom with a net positive charge. Likewise, another atom may receive a freed electron, which then makes the atom electrically negative. When we have two objects with different electric charges due to the absence or presence of excess electrons, we say that we have static electricity. We can demonstrate this using a balloon and a soda can. When I rub a piece of cloth against the balloon, I strip away electrons from the piece of cloth and add them to the balloon. As a result, this balloon now has a net negative charge. When we bring it close to the can chases the balloon. Let's look at why that's happening. The aluminum in the can is a conductor, which means that the electrons can freely move about the material. As we bring the negatively charged balloon near the metal, the electrons are pushed away to the far side of the can, since like charges repel. That leaves an excess of positive charge on the side of the can nearest the balloon, which is pulled toward the balloon as opposite charges attract. Since the positive charges are closer to the balloon than the negative charges, the attractive force is greater than the repulsive force. This results in a net force that pulls the can toward the balloon. Let's see that again in instant replay. Before we go any further, let's talk about units. The SI unit for electric charge is the coulomb, generally abbreviated with an uppercase C. An electron has a charge of about negative 1.602 times 10 to the negative 19th coulombs, and a proton has a charge of about positive 1.602 times 10 to the negative 19th coulombs. Energy is usually given in joules, which is abbreviated with the symbol uppercase J. 1 joule is equal to the amount of energy transferred to an object when a force of 1 Newton is applied to that object over a distance of 1 meter. Energy can either be potential, which results from an object's position or arrangement, or kinetic, resulting from the object's motion. Both kinetic and potential energy are given in joules. Now we can define voltage. Voltage is a measure of electric potential between 2 points. The unit, volt, is defined as 1 joule of potential energy per unit charge given in coulombs. Let's explain this with an example. Let's say that I've got a particle with a negative 1 coulomb of charge. Then, let's say there is a particle with positive 1 coulomb of charge next to it. Since opposites attract and the positive particle is as close as it can get to the negative particle, everything is at rest. There is no kinetic or potential energy. Now, let's say that I need to use 10 joules of energy to move the positive particle from its resting position to this point. If I were to release it, it would move back to the negative particle. As a result, we can say that it has 10 joules of electric potential energy so long as I hold it here. Now, if I repeated this demo with 3 positively charged particles, it would take 30 joules of energy to move them the same distance away from the negative particle. So they have 30 joules of potential energy as long as I'm holding them here. As we defined earlier, voltage is the electric potential between 2 points. To calculate the voltage between their starting and ending points, we know that I did 30 joules of work to move the particles, and the total charge is 3 coulombs. So the voltage is 30 joules divided by 3 coulombs, which is 10 volts. We would say that the electric potential between these 2 points is 10 volts. If I released one of the particles, it would move back to the negatively charged particle. That would leave me with 20 joules of potential energy and 2 coulombs of charge. So the potential is still 10 volts. Even if I had no positive particles, the potential between the 2 points is still 10 volts. As you can see, electric potential energy is not the same as electric potential. When we start talking about moving electrons through conductors and electronic components, we are talking about current electricity, which is slightly different than static electricity. Let's take a look at a battery. It doesn't really matter how far apart the terminals of a battery are. The chemicals inside a battery determine the electrical potential between the terminals. A fully charged AA alkaline battery is listed as having 1.5 volts. That means each coulomb of charge moving from one end of the battery will do 1.5 joules of work. Now, compare that to a much larger D-cell battery. Each coulomb of charge will still only do 1.5 joules of work, but a D-cell has far more coulombs of charge than a AA. As a result, D-cells will last a lot longer than AA batteries, doing the same amount of work. Static electricity can be a lot of fun, but more often than not, it's considered dangerous or a nuisance. One of the most dramatic displays of static electricity happens in nature. Storm clouds can build up a potential difference of millions of volts when compared to the Earth. And at some point, the electrons actually force their way through the air, creating lightning in order to balance out that charge difference. This sudden flow of electricity in an attempt to neutralize 2 statically charged objects is known as electrostatic discharge, or ESD. While lightning is a rather extreme display of electrostatic buildup and discharge, static electricity can still be quite useful. For example, many factory and power plant smokestacks employ a technology that uses static electricity to pull soot and ash out of the air as it flows up through the pipe, resulting in less pollution. Also, most cars are painted using a process called powder coating. In this, paint leaving the spray nozzle is given an electric charge, and the car body is given a different electric charge, which creates a stronger bond between the paint and the car body. This allows for a more uniform paint coverage and reduces paint waste, since less of it's likely to stick around in the air or drip off the car body. Next time, we'll dive into current electricity and talk about making it do work for us.
Well, thank you. Now, so let's dive back to the lectures. I want to now put the slide on again. So we've looked at a demonstration of what voltage is, and it's electrical potential or electrical potential energy that enables charge to do some work. And so you can define it as electrical potential between 2 points, or in other words, you can say it's work needed to move a test charge between 2 points. And therefore, mathematically, you can calculate that as work done in terms of joules of the amount of charges moved in terms of coulombs. Now, voltage is also referred to as electric potential difference, or sometimes it is referred as electric pressure or electric tension. So those are the two terms, not two, but a few terms used to refer to voltage. Now, let's talk about current, electrical current. What is electrical current? It's the rate of flow of charges through a conductor. We say current is that movement of charges through a conductor, and the charges mostly we are interested with are electrons through the conductor, and it is measured in units referred to as amperes. So 1 ampere can be defined as the amount of charges equal to 1 coulomb that would pass through a certain point in a conductor in 1 second. Or put differently, it is the amount of current produced by a voltage of 1 acting across conductor whose resistance is 1 ohm. So that's how we would then define current. Next, we have electrical resistance. And electrical resistance, you want to define it as the opposition to the flow of current. Now, in the water analogy, when water is flowing through the pipe, if you have a very thin pipe, then water flow will be restricted, and that represents a resistance. So the same kind of a scenario plays out in electrical circuits, where when electrons are flowing through a conductor, the conductor may exhibit some resistance against that flow, And that opposition is what we call resistance of a conductive element. Now, there is the reciprocal of resistance of a material is referred to as conductance. And first, resistance is measured in units of ohms, and conductance is measured in units of Siemens. So conductance is the reciprocal of resistance, and the two kind of tells the same information in different ways. So when you talk of resistance, you are talking of opposition to flow of charges. If you are talking of conductance, you are talking of how easily do charges flow through a conductor. So it's two things looked at different perspectives. Two same things looked at different perspectives. Now, the three quantities, that is the voltage, the current, and resistance, have a relationship. And this relationship is expressed in form of a physics law we call Ohm's law. And Ohm's law says that the current flowing through a conductor is directly proportional to the voltage across that conductive element, provided that conditions such as temperature and pressure are kept constant. So mathematically speaking, then you could write an equation, an expression like this, that V is proportional to I, where V represents voltage and I represents current. Now, you can put this expression in equation form, where then we say voltage is equal to a constant of proportionality multiplied by current. This constant of proportionality actually represents the resistance in that conductive element. So this then is the equation that we refer to as the Ohm's law. To help you understand the Ohm's law further, we have what we call Ohm's law triangle, where we have a triangle that is partitioned into three parts. The upper part is, we represent the voltage, then this side can put current, then this other side resistance. Now, what you are seeing here is that now the voltage being on the upper part of this triangle is given by multiplying current and resistance. So this triangle is kind of helping you remember very fast the relationship between voltage, current, and resistance. Same thing, you can use the same triangle, and from the equation itself, you can express if you wanted resistance in form of voltage and current. You can use this equation to do that, but also this triangle helps you to see them, to kind of verify whether your expression is correct. So current is given by the ratio of the voltage and the resistance, and resistance is given by taking the ratio of voltage and current. So the triangles kind of help you visualize those relationships very easily. Next, we look at what we refer to as electrical power, and what do we mean when we talk of electrical power? Power in physics is defined as the rate of doing work. Power is defined as the rate of doing work. Now, electrical power in a circuit is the rate at which energy is absorbed or produced within a circuit. A source of energy such as the voltage will produce or deliver power while connected load absorbs it. And examples of load, and we will be using this term load quite often, is the appliance that is absorbing the energy. So resistors, for example, will constitute will be categorized as the electrical load. If you put a bulb, for example, that would count as an electrical load, and so on and so forth. So a voltage source like a battery is generating the energy, and a load is absorbing that energy. So the rate at which you are either generating or absorbing electrical energy is what we refer to as power. We measure electrical power, we measure power generally in the unit referred to as watts. Now, if you want to calculate electrical power, what you do is you take the product of the voltage across the appliance that is either generating or absorbing power, and multiply that with the current flowing through it. So if it's a bulb, if you want to know how much power is being absorbed, then you want to measure the voltage across the two terminals of the bulb and the current flowing through the bulb. And that gives you the power that is being dissipated by this appliance. Now, we can relate electrical power with current, voltage, and incorporate Ohm's law to express either voltage or current in form of power. So, for example, we are saying power is the product of current and voltage, and here we have another triangle that we are putting P on the top of the triangle, then current and voltage, so that from this triangle you can see then if you want to calculate power, you need to multiply current and voltage. If you are interested in calculating current, then what you want to do is take power and divide it by the voltage. And if you want to calculate the voltage across an appliance, then you just need to know what is the power dissipated by the appliance divided by the current flowing through that appliance. So that's how you incorporate power in computing current and voltage in an appliance. Now, further, through simple algebraic manipulation, we can show that current can be given by the square root of power over resistance, or the ratio of power by resistance, or the ratio of voltage by resistance. All those expressions and give you current. And my recommendation is that you use Ohm's law and the definition of power to ensure that you derive all these equations and satisfy yourself that all these, you can show that all these relationships are true for current. Same thing for power. We have seen by very definition, power is the product of voltage and current. But again, by use of Ohm's law and some and the expression of power, you can show that it is given by the square of current by resistance, or the square of voltage and divided by the resistance of the appliance. It can also be shown that, and quite easily, that voltage is equal to the square root of power multiplied by resistance, and or voltage is equal to power divided by current. And when we are talking of this kind of relationship, I mean, you have to be talking of an appliance. You must have a circuit element in mind so that you ask yourself, what is the power dissipated or generated by that circuit element? Then divide by the current flowing through the circuit element. It could be a resistor, it could be a bulb, whatever it is. All these expressions are true when you are computing voltage, and using the definition of electrical power and Ohm's law, you can very easily show that this is the case. Same case for resistance. All these expressions in this portion of the pie chart gives expressions for computing resistance of a circuit. Now, while we are still talking about electrical power, every appliance, electrical appliance, has got a quantity or a specification we refer to as power rating. So what is the power rating of a device? It is the maximum rate at which the component converts electrical power into other forms of energy, such as heat, light, motion, etc. And in electrical circuits or in electronic circuits, we very often make use of resistors. But one thing you have to be keen about is the power rating of the resistor. Because if you happen to dissipate more power than the rating of that resistor, the device will go into smoke. So, and the same logic applies to every other electrical appliance. You have to ensure that its power rating, that is the maximum power that it can handle, is not exceeded. Otherwise, when you exceed it, you are going to blow up the appliance. So power rating is a very important specification, and to always keep in mind when you are dealing with electrical devices. It tells you how much power the device is able to handle. So if it's a 100-watt bulb, it means that that is the maximum power it can convert to light energy. Yeah, and things like that. So power rating is very important. And maybe what you want to do is ask yourself in your, let's say, your house, do you know the power rating of the appliances that you use? For example, a very common electrical appliance that almost every one of you always use is a phone. So have you ever asked yourself how much power, what is the power rating of your phone? Because at the end of the day, all these power ratings determine how much electrical energy you consume. That's the next thing we are going to. And the amount of electrical energy you are consuming determines how much electricity bill you pay. So you want to be very conscious of the appliances, the type of appliances that you are using. A case in point, you might, the kind of electrical bulbs you are using for writing might significantly affect how much you pay for your electrical bills. And at the end of the lecture, I will give you an exercise so that you compute how much it would cost if you used these energy efficient light bulbs we are calling LED bulbs. You go to the shop and you can buy it. Or if you decided to buy an incandescent bulb, the bulbs that we used to buy before the introduction of these energy efficient bulbs. So you want, the assignment will be, what is the cost of electricity in a month? How much would you pay if you are to use an energy efficient bulb? Or if you are to use an incandescent bulb? One thing is the incandescent bulb uses or cost less. In fact, a 100-watt bulb would cost you about 50 shillings. A right emitting diode with the equivalent output energy or output power would cost you about 200 to 300 shillings. Call it 300 shillings. But now when you put them side by side, how much would Kenya Power bill you for using an incandescent bulb and for using a right emitting bulb? So that is an assignment I would give you. Of course, let us assume you, on average, those two bulbs are on for, call it 3 hours a day. So in 13 days, how much would you have to pay for energy efficient bulb and this inefficient incandescent bulb? Now, to put our discussion in some formal definition, then we can say energy is the capacity to do work or It's the ability to do work. And you measure energy using units referred to as joules. Those are the SI units for quantifying energy. Now, how do you compute or how do you calculate electrical energy? Electrical energy is computed by taking the product of power dissipated by your appliance and then multiplying it with the time that that appliance is on. So electrical energy is power multiplied by time. Now power is in watts, time is in seconds. So you using that equation, you get electrical energy. Now, again, we can come up with a triangle that relates electrical energy in joules over power and time. So electrical energy in joules is given by power in watts multiplied by time in seconds. If you want to compute power, then you have to divide energy by time. And if you want to compute time, you have to divide energy in joules by power in watts. And then that gives you time in seconds. So mostly you want to work with the SI units. I think this is the same thing. Now, this another unit of electrical energy that is commonly used, and that is the kilowatt hours. Kilowatt hours. Instead of joules, you often electrical power is expressed in kilowatt hours. Now, what is it? You get energy in kilowatt hours if you multiply power in kilowatts. So you have, if you have power through a device, you have to convert it into kilowatts. Now, a kilowatt, 1 kilowatt is equal to 1,000 watts. Okay. So multiply that power expressed in kilowatts with time, but time in hours, not in seconds. So the product of power in kilowatts and time in hours gives you kilowatts. At first, it may not be obvious why we would use kilowatt hours as opposed to joules, but the reason is to ensure that the numbers, as far as electrical energy is concerned, remains small, because they can very easily become astronomical, very big, if you are working with joules as opposed to kilowatt hours. A simple example that I would wish you to do calculation on your own is, assume you are using a 100 watt bulb, and you are operating it for 13 days, 3 hours per day, and you are asked to calculate energy in joules. Total energy used in joules in 1 month. Then what you would need to do is say, this is very easy. Energy is power times time in second. Power in watts, time in second. So our power is 100 watts. And time, now we have to convert these 13 days. Each day you are operating it for 3 hours. So you have to convert that to seconds. And that becomes a very big number. That becomes a very big number. And so you see, if the electricity utility company is to now express that all appliances used, we would be dealing with very large numbers, which is inconvenient and cumbersome. So to ensure that we are dealing with relatively small numbers, that's the need of using these units of kilowatt hours. Becomes a smaller number, but more or less is the same thing expressed in a different way. So I think with that we can stop at that point, and the next lesson will be on Kirchhoff's law. Thank you.